here is a very useful trick for evaluating Laplace transforms of power functions. And in fact, let's use this to calculate the Laplace transform of t cubed, which I like to remind you is the integral from 0 to infinity of t cubed e to the minus st dt. And what I'd like to show you is a technique called tabular integration, or it's also sometimes called the DI method. And what it really is, it's a shorter way of doing a bunch of integrations by parts. And the way it works is as follows. On the left-hand side, you put t cubed. On the right-hand side, you put e to the minus st. And then for the t cubed column, you just differentiate as many times until you get 0. So here you differentiate and you get 3t squared, and then derivative of 3t squared is 6t, and then 6, and then bam, we have 0. For e to the minus st, you anti-differentiate as many times until you reach the 0 line. So here we have e of minus st, and then you anti-differentiate to get e of minus st over minus s, and then you do it again, e of minus st over minus s squared, e of minus st over minus s cubed, and then e of minus st over minus s to the 4th. I know it looks very weird, but you'll see it's always the same. And then you put a bunch of pluses and minuses. So you start with plus, and you alternate minus, and then plus, and then minus, and then plus. That's because in integration by parts, you get uv minus integral v du. So the signs alternate. And almost done, I promise. Then you just consider the diagonal terms, but with those new signs. Kind of think cross-multiplying. And finally, you can evaluate your integral as follows. So the Laplace transform of t cubed, what it becomes, it's plus t cubed times the diagonal term e of minus st over minus s, and then minus 3t squared times e of minus st over minus s squared, and then plus, I believe, 60 times e of minus st over minus s cubed, and then finally minus 6 times e of minus st over minus s to the 4th. And you evaluate this simply from t equals 0 to t equals infinity. And that's because, remember, it's an integral from t cubed, from 0 to infinity of t cubed e of minus st. Now, as horrible as this looks, it's actually not too bad, because remember, first of all the terms at infinity are 0. So we have 0, minus 0, plus 0, minus 0. And then for the t terms, most of them are 0, right? T cubed at 0 is 0 cubed, and then times whatever, minus 3 times 0 squared, plus 6 times 0, minus 6 times e of minus s times 0 over minus s to the 4th. And once the dust has cleared, we get 6 times 1 over s to the 4th, and so 6 over s to the 4th. So in other words, the Laplace transform of t cubed is 6 over s to the 4th. And well, you can actually generalize this. So what about the Laplace transform of t to the n? How is 6 related to 3? Actually, if you do the calculation, 6 is really 3 times 2 times 1, which is really 3 factorial. And then how is 4 related to 3? It's 3 plus 1. So in fact, Laplace transform of t to the n just becomes n factorial over s to the n plus 1. Which, once again, you can take as a given unless I tell you to calculate it, which I've done on one example.